Good day everyone, I'm here to report about the duration of unit hydrograph. The choice of the duration of unit hydrograph on the rainfall records if the recording rain gauge data are available in any convenient time depending on the size of basin can be used. The right guide for the choice of duration D is that it should not exceed the list of the time of rise, the basin lag, and the time of concentration. The value of D is equal to about one-fourth of the basin lag is about the best choice. Generally, the basin with area more than 1,200 kilometers squared, duration D equal 12 hours is prepared. Our next topic is duration graph. Our next topic is duration graph. The distribution graph introduced by Bernard 1935 is a variation of the unit hydrograph. It is basically a DH unit hydrograph which ordinates showing the percentage of the surface runoff occurring the successive period of equal time interval of DH. The duration of rainfall exists. DH is taken as the unit interval and distribution graph ordinates the indicated at successive such unit interval. In figure 6.19 show a typical 4S distribution graph. Note the ordinate plotted at 4H interval and the total area under the distribution graph adds up to 100%. The use of the distribution graph to generate a direct run of hydrograph for a new effective rainfall hydrograph is exactly the same as that of a unit hydrograph. Distribution graphs are useful in comparing the runoff characteristic of different catchment. Our next topic is synthetic unit hydrograph. To develop unit hydrograph to a catchment, detailed information about the rainfall and the result flooding hydrograph are needed. Those such information would be able only at a few locations and in a majority of catchment, especially those which are at remote location. The data would normally be very scanty. In order to construct unit hydrograph for such areas, empirical equation of regional validity which relate the silent hydrograph characteristic to a basin characteristic are available. Unit hydrograph derived from such relationship are known as synthetic unit hydrograph. A number of methods for developing synthetic hydrographs are reported in literature. Our next topic is Snyder method. In this video, it explains its definition and methods.
In 1938, based on a study of a large number of catchments in the Appalachian highlands of eastern United States, developed a set of empirical equations for synthetic unit hydrographs in those areas. These equations are in use in the USA and with some modifications in many other countries, and constitute what is known as Snyder's synthetic unit hydrograph. The most important characteristic of a basin affecting a hydrograph due to a storm is the basin lag. While actually basin lag, also known as lag time, is the time difference between the centroid of the input. What is input? The rainfall excess is the input and the output, direct runoff hydrograph. I will repeat the sentence. While actually basin lag, also known as lag time, is the time difference between the centroid of the input, rainfall excess, and the output, direct runoff hydrograph, because of the difficulty in determining the centroid of the direct runoff hydrograph, DRH. It is defined as, for practical purpose, it is defined as the elapsed time between the centroid of rainfall excess and the peak of DRH, peak of direct runoff hydrograph. That particular time, it is considered as the basin lag or lag time. For practical purpose, the time elapsed between the centroid of rainfall excess, ER, and the peak of DRH, it is considered as the basin lag. So you can see here, this is what the basin lag, the time elapsed between the centroid of the rainfall excess to the peak of the DRH. It is considered as the basin lag, denoted by letter T suffix P. Physically, lag time represents the mean time of travel of water from all parts of the watershed to the outlet during a given storm. Its value is determined essentially on the topographical features such as size, shape, stream density, length of the main stream, slope, land use and land cover. The modified definition of basin time is very commonly adopted in the derivation of synthetic unit hydrographs for a given watershed. So this is what the modified definition that we have seen. It is used to derive the synthetic unit hydrographs for a given watershed. So this is a typical hydrograph showing the elements of a synthetic unit hydrograph. You can see various parameters over here, like time on x-axis, discharge on y-axis. You can see that demarcation of W50, W75 over here. This QP represents the peak discharge. This is the total time duration of the DRH, TB. This is the 1 centimeter rainfall. This is the rainfall duration. This is the lag time. This is the timing between the starting of the rainfall up to the peak occurrence. And these values are the 50% of the peak discharge value, and this is the 75% of the peak discharge value. Okay, so let us understand what is given and what is to be estimated, how these hydrographs will in turn help to develop new hydrographs for a geographically similar catchments. The first of the Snyder's equation relates the basin lag TP. The basin lag TP, defined as the time interval from the midpoint of the rainfall axis to the peak of the unit hydrograph. As you can see, the basin lag TP, defined as the time interval from the midpoint, from the midpoint of the rainfall axis to the peak of the unit hydrograph. It is the basin lag. To the basin characteristics, as it can be estimated by using this empirical formula given by the Snyder as TP is equal to CT into bracket L into L suffix Ca whole bracket raised to 0.3, where TP is the basin lag in hours, capital L is the basin length measured along the water course from the basin divide to the gauging station in kilometers, L suffix small ca is equal to distance along the main water course from the gauging station to a point opposite to the watershed centroid in kilometer. Usually these values of L and LCA will be given to you while solving the numerical. Ct, C suffix T is equal to a regional constant representing watershed slope and storage effects. You have to estimate this Ct. The value of Ct in Snyder's study ranged from 1.35 to 1.65. However, studies by many other investigators have shown that Ct depends upon the region under study, and wide variations with the value of Ct ranging from zero point 0.3 to 0.26 have been reported. Linsley, etc. all found that the basin lag Tp is better correlated with the catchment parameters as into bracket L into LCA divided by under root of S, where S is the basin slope. Hence, a modified form of equation was suggested by them to find out the basin lag. Tp is equal to C suffix TL into bracket L into LCA divided by under root of S whole bracket raised to N, where CTL and N are the basin constants. You can use this equation to find out the basin lag. Snyder adopted a standard duration TR hours, T suffix small r hours of effective rainfall given by TR is equal to TP upon 5.5. That is the standard duration of effective rainfall is equal to basin lag TP upon 5.5. The peak discharge QPS meter cube per second of a unit hydrograph of standard duration TR hours is given by Snyder as QPS, that is peak discharge of a standard duration rainfall for a unit hydrograph is equal to 2.78 Cp into A upon Tp, that is basin lag, where A is the catchment area in kilometer square and Cp is a regional constant as we have seen. This equation is based on the assumption that peak discharge is proportional to the average discharge of 1 centimeter into catchment area divided by duration of rainfall excess. If a non-standard rainfall duration T suffix capital R hour is adopted instead of the standard value of T suffix small r to derive a unit hydrograph, the value of the basin lag is affected. Therefore, the modified basin lag in that case where the non-standard duration rainfall it is considered, the modified basin lag T dash P is given by the formula T dash P is equal to Tp plus T suffix capital R minus small t suffix small r divided by 4, which is further simplified as 21 by 22 times Tp, that is basin lag, plus T suffix capital R divided by 4, where T dash P is equal to the modified basin lag in hours for an effective duration of TR, T suffix capital R hours, and TP is given by the earlier equation. You can find out the value of TP by earlier any of the equation. This is the equation to derive the value of TP, or this equation you can use to find out the value of TP. The value of T dash P modified basin lag must be used instead of Tp in the equations further. Thus, the peak discharge, for the measurement of peak discharge, you can see peak discharge, it has the value of Tp over here. So you will use the value of T dash P instead of Tp if there is a non-standard duration rainfall. So the peak discharge for a non-standard rainfall excess of duration T suffix capital R is in meter cube per second. Q suffix p is equal to 2.78 Cp into A upon T dash P. Rest of the terms will remain same. Just instead of Tp, here the value of T dash P will reflect. Note that when Tr is equal to small t suffix small r means what? The non-standard duration, if it is equal to the standard duration, then the peak discharge in both the cases will be same. The time base of a unit hydrograph is given by Snyder as capital T suffix small b. This is time base of the unit hydrograph. It is given by the Snyder as 3 plus T dash P upon 8 days, which is further simplified as 72 plus 3 into T dash P hours, where TB is the time base, while above equation gives a reasonable estimate of TB for large catchments. It may give excessively large values of the time base for small catchments. Taylor and Schwartz recommend for small catchments the value of TB, that is time base, can be estimated by the formula capital T suffix small b is equal to 5 into bracket T dash P plus T suffix capital R divided by 2 hours, with TB given in hours taken as the next larger integer value divisible by T suffix capital R, that is TB time base is about 5 times the time to peak. To assist in the sketching of unit hydrographs, the widths of unit hydrographs at 50 and 75% of the peak have been found for US catchments by the US Army Corps of Engineers. These widths in time units are correlated to the peak discharge intensity and are given as per the following formulas. So first of all, you will need to find out the W50 width of this particular unit hydrograph at this particular 50% peak discharge value. You have to estimate first of all the peak discharge, then at the 50% of the peak discharge value, whatever the width of hydrograph you are going to obtain, that can be obtained by this empirical formula 5.87 divided by q raised to 1.08. After finding out the width at 50% peak discharge, you can find out the width of hydrograph at 75% peak discharge by the formula W50 upon 1.75. If you know the width at 50%, you can find out the width at 75% of the peak discharge, where W50 is the width of the unit hydrograph in hours at 50% peak discharge, and W75 is equal to width of the unit hydrograph in hours at 75% of the peak discharge, where this small q is equal to q suffix p divided by a. So this is peak discharge per unit area. Which area? This is the peak discharge per unit catchment area in meter cube per second per kilometer square. If you know the catchment area, you can easily find out the value of small q. Since the coefficients Cp and Cp vary from region to region, in practical applications, it is advisable that the value of these coefficients are determined from known unit hydrographs of a meteorologically homogeneous catchment and then used in the basin under study. This way, Snyder's equations are of use in scaling the hydrograph information from one catchment to another similar catchment. If you know the parameters for one catchment, you can extend those similar parameters to other catchment to know how the with the help of empirical formulae to know how the construction of unit hydrograph can be done for further studies. So with the help of numerical example, we will see how the coordinates, rather various parameters of a synthetic unit hydrograph of by the Snyder's method can be estimated. Here two catchments are given in the example. Two catchments A and B are considered meteorologically similar. This word is important. You can apply the Snyder's method only if the catchments are meteorologically similar. Two catchments A and B are meteorologically similar. Their catchment characteristics are given below. So in the table you can see there is a catchment A and catchment B. As usual in the numerical the values of lengths are given L, LCA and the areas of both the catchments are given. For the catchment a 2-hour unit hydrograph was developed and was found to have a peak discharge QP of 50 meter cube per second. The time to peak from the beginning of the rainfall excess in this unit hydrograph was 9 hours, that is capital T suffix P, total time from the beginning up to the peak. Using Snyder's method, develop a unit hydrograph for the catchment B. So in detail, the various parameters for catchment A is given and you are asked to find out a unit hydrograph. You have to develop a unit hydrograph for the similar catchment B. So in the solution for catchment A, we have to first of all find out various parameters by the given data. As you can see, TR it is given, that is non-standard duration of the rainfall, it is 2 hours. Then time to peak from the beginning of excess rainfall, it is given as 9 hours. So by putting the values in this equation, Tp is equal to Tr by 2 plus Tp dash is equal to 9 hours, you can find out this basin lag, rather modified basin lag as 8 hours over here. After getting this T dash P, you can put this T dash P in the equation. T dash P is equal to 21 by 22 Tp plus T suffix capital R by 4 is equal to 21 by 22 Tp plus 0.5. You can get it as get the value of Tp, that is basin lag, as 7.857. This basin lag it is for the standard duration. Since Tp is equal to Ct into bracket L LCA raised to 0.3, you can put the values over here and you can find out the value of Ct from the estimated value of Tp. You can find out this particular parameter Ct constant. Then from the equation peak discharge is equal to 2.78 Cpa divided by T dash P, you can find out the value of this Cp. It will come out as 0.576. So now you have got these constants which are similar for the catchment B as well. We have to use these particular Ct and Cp values to estimate the various parameters for the catchment B, because these are the geological factors. Now for catchment B, you will use the same values of Ct and Cp as estimated for catchment A. So using the values of Ct as 1.257 and Cp as 0.576 in the catchment B, the parameters of the synthetic unit hydrograph for catchment B are determined. From equation Tp is equal to Ct L LCA raised to 0.3, you can find out Tp by putting all the values. You can get it as 10.34 for catchment B. Here the L and LCA for catchment B they are given. L is 45, LCA it is 25, 45, 25. You can get the value of Tp for catchment B, that is basin lag. Then by equation Tr is equal to Tp upon 5.5, you can estimate the value of Tr, that is standard duration of the rainfall excess, it is 1.88 hours. Then using T suffix capital R is equal to 2 hours, that is for 2-hour unit hydrograph, by equation T dash P is equal to Tp plus Tr minus Tr by 4 is equal to 21 by 22 Tp plus Tr upon 4. You can put the values and you can estimate the modified basin lag for the catchment B. It will come out as 10.37 hours. Now by the equation peak discharge, you just have to put the values. You will put the basin lag as a modified basin lag T dash P over here, and you can estimate the peak discharge as 61.77 meter cube per second, which is approximately equal to 62 meter cube per second. Once you get the peak discharge, you can find out the small q. Small q is what? Peak discharge per unit catchment area. So to estimate the value of W50, you will need to find out this Q. Q is this capital Q divided by area of the catchment. Area of the catchment it is given as 400. So W50 is equal to 5.87 Q raised to 1.08. So W50 it is equal to 5.87 divided by 62. This 62 divided by 400 raised to 1.08, which will come out as 44 hours. This is the width of the unit hydrograph for catchment B at peak discharge equal to 50% value. Now, when you get the W50 width of the hydrograph at 50% peak discharge, you have to estimate the width of the hydrograph at 75% peak discharge. So, by dividing the W50 by 1.75, you can estimate the W75 as 25 hours. So, time base from equation Tb is equal to 3 plus T dash P upon 8 days. It is equal to 72 plus 3 into T dash P hours. By putting the value of T dash P as 10.37 modified Bayesian lag, it will work out as 103 hours. And from other equation, we have seen the value of, we have seen Tb, it can be estimated by these two equations. This is for the larger catchment and this is for a smaller catchment. So if you put the values in this second equation, it will yield the value of Tb, that is time base, as 58 hours. Now if you look at the areas of both the catchment, catchment A is smaller and catchment B is larger one. Okay, considering the values of W50 and W75, W50 and W75, and noting that the area of catchment B is rather small, then you can have this particular TB for plotting of the unit hydrograph. TB it is equal to 58 hours is more appropriate in this particular case. It is a judgmental one. Then finalizing of unit synthetic unit hydrograph. After getting the values of all these parameters, you have to plot the unit hydrograph, rather synthetic unit hydrograph. After obtaining the values of QP, that is peak discharge, TR, T dash P, W75, W50 and TB from Snyder's equations, a tentative unit hydrograph is sketched and S curve is then developed and plotted. As the ordinates of the unit hydrograph are tentative, the S curve thus obtained will have kinks. These are then smoothened and a logical pattern of S curve is sketched. Using this S curve, TR, our unit hydrograph, is then derived back. Further, the area under the unit hydrograph is checked to see that it represents 1 centimeter of runoff. The procedure of adjustments through the S curve is repeated till satisfactory results are obtained. It should be noted that out of the various parameters of synthetic unit hydrograph, the least accurate will be the time base capital T suffix small b, and this can be changed to meet other requirements.